All right. Just saying. Okay, so we're dropping this object, and obviously it doesn't drop at its fastest speed, right? So your speed is increasing as it's going towards Earth. Okay, speed is increasing. As a result, your height here, as it's falling, your height is decreasing, right? Your height is decreasing at a faster and faster rate. As your height decreases, your height, actual height, is falling faster. So it's kind of like you have to kind of understand what's going on for this math to apply and to make sense. And that's why physics courses really does help understand the math. They really tie in together when you start getting in your junior and senior years. Okay. In fact, math is used to prove a lot of the physics concepts. So that's what all this is saying. The height and speed of the object t seconds after it drops can be modeled by the function, and we've used this function before, right? We just don't have the velocity term. Okay. The v sub o plus t, right? Or v sub o t. Where the h of o is the initial height, we know that. This model assumes that the force of air resistance on the object is negligible. Unless, of course, the object's like a feather and it does have air resistance, right? And they want to stipulate that this model works only on Earth. Can't work on the moon or anything because there's no gravity. We would have to take out that gravity constant. So you guys ready to do a problem?
Yeah.
Good. A stuntman working on a set of a movie is to fall out of a window 100 feet above the ground. So again, I'm going to draw my picture, might as well. So here's my height. Here's the time. So this guy, starting here at 100 feet. Bless you. You're welcome. Okay, so he's falling out of a window. For the stuntman's safety, an air cushion 26 feet wide by 30 feet long by 9 feet high is positioned on the ground below the window. Oh, I can zoom out a little bit. How about that? Better? Okay. Again, it's different on my computer screen than the overhead, so thank you for letting me know. For how many seconds will the stuntman fall before hitting the cushion? All right. So let's pick out a few things. This was my initial height, right? 100 feet. That's my h of 0, my initial height. Okay, now this whole air cushion thing. I really don't care how wide it is and how long it is because I'm in 2-dimension here. I'm worried about how high it is. It's 9 feet high. So he's not going to hit the ground. He's going to hit here at 9 feet, right? So he's going to hit here. Now here's my picture. Boom. Okay, so for how many seconds will the stuntman fall before hitting the cushion? So we're looking for this time here, right? All right, let's go ahead and get our equation, right? Our equation is h equals negative 16t squared plus h of 0. Okay, so the current height here, that's going to be his 9 feet. That's where he's going to end up, right? That's going to be his current height, 9 feet. Equals our gravity constant, negative 16. We're trying to find the t, so that's still going to be a t squared. But we do know the initial height, right? That's 100. Okay. All we have to do is solve this quadratic equation. Now, since we just learned square rooting, right? Solve by square rooting. Let's do that. Because I think you guys probably like that better than factoring. So I need to get the t squared by itself. So the first thing I'm going to do is subtract 100 from both sides. Okay. I'm going to go up here. So 9 minus 100 is negative 91, right? Equals negative 16t squared. And these hundreds cancel out to 0. Okay, almost there. Almost got the t squared by itself. I need to take away that coefficient, that gravity coefficient, right? Gravity constant. So I'm going to divide both sides by negative 16. All right. Negative 91 negative 91 divided by negative 16. And what'd you get? 8. So 5.7. Okay, so we get 5.7 equals t squared. And I got to get rid of the power 2, right? So I'm going to square root both sides. That's what I didn't do last hour. I didn't take the square root. Okay, so I get t is going to equal plus or minus the square root of 5.7. Now, since this is a word problem, I'm going to go ahead and get an approximation here. I'm going to get a decimal. So I'm going to take the square root of 5.7, hit enter, and I get t is going to equal plus or minus. I'm going to leave the plus or minus out because I'll tell you what, we can't have a negative time. For a word problem, I don't need the negative. So I got 2.39. Approximately, I should use approximately 2.39 seconds. Little squiggly lines there. All right. That was fun.
In this instance, we don't need to do positive and negative, right?
Right, because we're talking time. Negative time doesn't exist in our world yet. Okay, so there's the answer to the problem. About 2.4 seconds. Part B, a movie camera operating at a speed of 254 frames per second records the fall. How many frames of the film show the stuntman falling? So we have 254 frames per second, and we got about 2.4 seconds, right? So let's go ahead and figure this out. So I have about 2.39 seconds. Good. Times 254 frames per second, right? So I'm going to put this over 1 because we have fractions here. All right, so I cancel out the labels. Remember doing this? If you have Algebra 1, you should have been doing it. And then we did, if you have chemistry, you do a lot of that too. So I'm going to end up with, let's see, frames on top. And I don't even need a fraction, okay? So I'm going to take 2.39 so I'm going to take my answer here, multiply it by 254, and that's going to give me about 606 frames. There's my answer. That was so much fun. You guys want to do the next one? Why not? Use, you see, you said thanks, so I'm going to go ahead and do it. Now, if you said, yes, I positively have it, then I wouldn't do it. Use the following object model. H equals negative 16t squared plus s, where t is measured in seconds and h is measured in feet, to find the time required for an object that is dropped from a height of s equal 100 feet and s equal 200 feet. Does an object that is dropped from twice as high take twice as long to reach the ground? Ooh, that's kind of interesting. I don't know. What do you guys think?
We're kind of setting up two different problems here.
Yeah, but it's actually a pretty good problem. We're going to drop one at 100 feet and then one at 200 feet. Do you think it's going to take twice as long at 200 feet? What's your common sense telling you? Your common sense says, well, it's twice as high, so it should take twice as long to hit the ground, right? But you're in math class, and nothing's common sense about math class, right? Okay, so let's do our formulas, right? So the ground is 0 feet, right? So 0 equals negative 16t squared. This one's going to be plus 100. And then this one is going to be 0 equals negative 16t squared plus 200. Because this one's 200 feet, we start, and this one's 100. Let's see if these does indeed take twice as long. Okay, subtract 100. Subtract 100. So I get negative 100 equals negative 16t squared. Divide both sides by negative 16, negative 16. What is that? 1.6. 100 divided by negative 16. .25 equals t squared. And then I have to take the square root, right? And again, I'm not going to worry about the negative this time because it's time. And that gives me about 2.5 seconds. So t is going to equal 2.5 seconds. Let's see, 2.5 seconds. right, let's solve the other one. See, subtract 200. Subtract 200. This is good practice for you guys. I like this problem. Negative 200 equals negative 16t squared. Divide by negative 16, negative 16. Let's see, 200 divided by 16, 12 and a half. So 12.5 equals t squared. I have to take the square root of both sides. Not going to worry about the negative because it's time. Square root of 12.5, 3.5. So 3.5 seconds. Okay. Compare the two. It's not double, is it? Cool. It actually only takes about a second longer. Huh. I did not know that.
Well, without air resistance,
right? Right. That's pretty interesting. I might have to take physics. All right, any questions? Let me show you.